Concept learning. A concept is a category used to group similar events, ideas, objects, or people. Concepts are abstractions. They do not exist in the real world. They only individual examples of concept exist. Concepts help us organize vast amounts of information into manageable units. Example, according to Bruner, a very, very famous psychologist. So according to him, there are about 7.5 million distinguishable differences in colors. By categorizing these colors into some dozen or groups, we manage to deal with this diversity quite well. Right? So isn't that crazy? But we could, by doing this here, we could differentiate about 7.5 million differences in colors. But by the way, women are much, much better than men in this regard. Okay, so you never argue with a woman about color. Okay, I learned it the hard way. You tell my wife this, you die. Okay. All right, let's take a look at what views of concept learning. All right. So traditionally, psychologists have assumed that members of a category share a set of defining attributes or distinctive features. Right? So students all study. Books all contains pages that are bound together in some way. Right? So since about the 70s, however, these long popular views about the nature of concepts have been challenged. While some concepts such as equilateral triangle have clear-cut defining attributes, most concepts do not. So take the concept of party. You like going to party, do you? Okay. What are the defining attributes? You might have difficulty listing these attributes, but you probably recognize a party when you see or hear one. Well, unless, of course, we are talking about political parties or the other party in a lawsuit where the sound might not help you recognize the party. Well, what about the concept of a bird? Your first thought might be that birds are animals that fly. But is an ostrich a bird? Well, what about a penguin? Bat? Okay. That kind of thing, all right? So according to critics of traditional view of learning, we have in our minds a prototype. Okay? We have in our mind a prototype of a party and a bird, an image that captures the essence of each one concept. All right? Now, but then take a look here. A prototype is the best representative of its category. At the boundaries of a category, for example, we now know that dinosaurs evolved into birds. It may be difficult to determine if a particular instance really belongs, or whether something fits into a category is a matter of degree. Thus, categories have fuzzy boundaries and graded membership. So another example of concept learning suggests that we identify members of a category by referring to exemplars. Exemplars. Now, exemplars are our actual memories of some specific examples of concepts that we can use to compare with an item in question to see if that item belongs in the same category as our exemplar. Now, prototypes probably are built from experiences with many exemplars. This happens naturally because, well, episodic memories, remember episodic memories, the conveyor belt phenomenon. Okay? The episodic memories of particular events tend to blur together over time. As the event is leaving us, in the conveyor belt to far, far away. So creating an average or typical bird from all the bird exemplars you have experienced. Now, in addition to prototypes and exemplars, there is a third element involved when we are recognizing a concept. Our semantic knowledge related to the concept. For example, how do we know that counterfeit money is not real money, even though it perfectly fits our money prototype and exemplars? We know because our understanding of the concept money is connected with concept of crime, forgery, the Federal Treasury, and what? Many others. So strategies for teaching what? Concepts. Take a look. How do we do that? Educators have trouble doing this. Is that right? And what? Especially for new teachers. Now, most of the current approaches to teaching concepts still rely heavily on the traditional analysis of defining attributes. Interest is growing, however, in the prototype's view of concept learning, partly because children first learn many concepts in the real world from best examples or prototypes pointed out by adults. So one approach to teaching concepts is called concept attainment. Concept attainment, a way of helping students construct an understanding of specific concepts and practice thinking skills such as hypothesis testing. Of course, here children will have to be in the Piaget's formal operational stage. An example will be readily edible food versus raw meat, or things that are not palatable So let's take a look at what, say, some strategies for teaching concept. Lesson components. Whatever strategy you use for teaching concepts, you will need 4 components in any lesson. Okay, let's take a look at what all these 4 components. First of all, examples and non-examples. So examples are essential in teaching concepts. More examples are needed in teaching complicated concepts and in working with younger or less able students. Both examples and non-examples, sometimes called positive and negative instances, are necessary to make the boundaries of a category clear. So a discussion of why a bat, this is a non-example, is not a bird, will help students define the boundaries of the bird concept. As a bat is not a bird. Okay? And similarly, Dumbo is not a bird. All right. Anyway, second, the identification of relevant and irrelevant attributes. The ability to fly is not a relevant attribute for classifying animals as birds. Okay, even though many birds fly, some birds do not. Okay, ostrich, penguin, and some non-birds, they do fly. Bat, flying squirrels, and of course Dumbo. Now, so then the name of the concept, okay, is important for communicating, but it is somewhat arbitrary. Is that right? The name is just a label we want attached to the thing or to the bird. Okay? Simply learning a label does not mean the person understands the concept, although the label is necessary for understanding. Okay, all right. Now, number 4, a definition. We have a lot of time we have definitions, is that right? A definition makes the nature of the concept clear. A good definition has 2 elements. Okay. First, a reference to any more general category that are that the new concept falls under. And then B, a statement of the new concept defining attributes. For example, a fruit is food we eat, that general category, with seeds in the edible parts, that defining attributes. Okay. An equilateral triangle is a plane, simple, closed figure. So plain, simple, closed figure. Okay, so that's general category. With 3 equal sides and 3 equal angles. So that's the defining attribute. So I hope that this will bring back your high school or geometry, okay? All right, so in teaching some concept, a picture, of course, is worth 1,000 words. We know that. And that's why, remember when we discussed our level of processing, if we process the semantic aspect of the word, let's say, yes, the processing is deeper than if we process the phonemic aspect or the structural aspect. Then Alan Pavio showed that one, if we process the imagery, that is the picture, well, our memory for that one is even what the strongest. All right. So a picture is worth 1,000 words. Right? And what it has been found that when the students were the student just read about concept, only 20% could understand the role of refracted light in our ability to see objects. But when the students worked with diagrams, almost 80% understood the concept. So let me show you this. It is, I just want, this is so bad, but then in my slide, it is good anyway. So this is a person, this is a tree. I will try to find this thing, and then I'll send it to you. If I forget, remind me. So the way we see the tree is because what? Because of sunlight here, that reflection. Okay, well, reflect the sunlight, so therefore we see the tree. This one here is not that bad. This is what this picture before I translated into PDF. But anyway, let's move on. Lesson structure. It is more effective to examine examples and non-examples before discussing attribute or definitions. Okay, so you start the concept lesson with prototypes or best examples to help the students establish the category. Now, using various examples helps prevent undergeneralization or the exclusion of some members from their rightful place in the category. And you give information to help students avoid focusing on an irrelevant attribute as a defining feature. Now, non-examples should be very close to the concept, but missed by one or just a few critical attributes. Okay. Including non-examples will prevent overgeneralization or the inclusion of non-members as a category. Now, after the students seem to have grasped the concept under consideration, it is useful to ask them to think about the ways that they formed and tested their hypothesis. Thinking back helps students develop their metacognitive skills and shows them that different people approach problems in different ways. Now, Remember metacognitive skills. That is one, metacognition, thinking about our thinking. All right, so that is important. All right, and extending and connecting concept. Once students have good sense of a concept, they should use it. This will connect the concept into the students' web of related semantic knowledge. One approach is concept mapping. Students will diagram their understanding of the concept. Right? So it is one. It is good. All right. When we do that, let me, where is that? Okay. All right. I think I got this. Okay, hold on. Let's see. All right. See here, when the light strikes the tree, it helps the girl to see the tree. How does it do it? Okay. When sunlight strikes the tree, it helps the girl to see the tree because some of the light bounces or is reflected off the tree and goes to the girl's eyes. Right? So that's how we see things. Right? That's how we see things. Wow, this one. Look at it. This is my one. I use the document camera, so it serves as what it serves as a whiteboard. Okay, and I could do this. Right? So let me put this thing back. Okay, hold on. Where do I put it? Okay, hold on. All right. Okay, good. All right. Problem solving. All right. Are problem solving strategies specific to the problem area? Problem solving in mathematics are unique to mathematics. The strategies in art are unique in art, okay? Or some general problem solving strategies that can be useful in many ways. Perhaps we could do that. Okay. Now, so this is something one. I think this is something we can one. We do here is that one. We have, can I see it? Yeah, I can see. All right, so we have one. I do have this. Now, let's say we have a new domain. Then what we can do this here, all right? All right. So if the general learning what problem solving strategies can apply to this, beautiful. But if we cannot here, we will have to develop for someone. Okay, somewhat specific strategy, some specific strategy from here. Therefore, what? Then we will be okay. A lot of time, a lot of time we do this here, right? So there is evidence for both sides of the argument. In fact, it appears that people move between general and specific approaches depending on the situation and their level of expertise. So early on, when we know little about a problem area or a domain, we may rely on the general problem solving strategies to make sense of the situation. As we gain more domain-specific knowledge, particularly procedural knowledge about how to do things in the domain. Remember procedural memory, the action doing. We need the general strategies less and less. But if we encounter a problem outside our current knowledge, we may return to relying on general strategies to attack the problem. So a lot of time, we will rely on this, apply this to the new domain, and we generate specific strategies which could be applied to similar problems. Okay, that is in general how we want solve problem. Right? So take a look at what's some general problem solving strategy. Frankfurt and Stein used the acronym IDEAL to identify 5 steps. So it is easy to memorize the acronym, right? So first, identifying that a problem exists and treating the problem as an opportunity begins the process. All right. So that's what, first of all, we have to identify that there is a problem. Okay, defining goals and representing the problem. Now, let me give you an example. The machine designed to pick tomatoes are damaging the tomatoes. So what they do? If we represent the problem as a faulty machine design, the goal is to improve the machine. But if we represent the problem as a faulty design of the tomatoes, then the goal is to develop a tougher tomato, like tougher skin. So the problem-solving process follows 2 entirely different paths, right? Depending on which representation and goal are chosen. To represent the problem and set a goal, you have to focus on relevant information, understand the elements of the problems, and activate the right schema to understand the whole problem. And of course, here I will come back to the machine picking tomato. I will come back to this example when we discuss intelligence, IQ. Right, so first of all, here, focus what? Focusing attention. Representing a problem often requires finding the relevant information and ignoring the irrelevant details. Now, so Sternberg, and I will use this one example in IQ testing. Okay, say if you have black socks and white socks in your drawer, mixed it in the ratio of 4:5, how many socks will you have to take out to make sure of having a pair the same color? All right. Now, what information is relevant to solving this problem? You have what? Black and white socks makes the 4:5. Okay, so did you realize that what the information about the 4:5 ratio of black socks to white sock is irrelevant? Okay, the answer would be the same if you have what? 1:3, 2:5, or 2:100. Anyway, that type of thing, right? So as long as you have only 2 different colors of socks in the drawer, you will have to take out only 3 socks before 2 of them have to match. So this is an IQ test question from Sternberg, Robert Sternberg. This is what the test was. To test something school has never taught you. Okay, all right, let's move on. Understanding the whole problem, okay? Or understanding the words, linguistic comprehension, okay? Understanding the meaning of each sentence. For example, the river boat's rate in still water is 12 miles per hour, more than the rate of the river current. So see here, this is what? This is the relational proposition. It describes the relationship between 2 rates. All right. So it's the speed of the boat and the speed of the current. Okay. Now, the cost of oranges is what? 1.99 per pound. This is an assignment proposition. It simply assigns a value to something. Right? It assigns a value to something. All right. Understanding the whole problem. Okay. But before we do that here, let me talk about what relational and assignment proposition. Research has shown that relational propositions are harder to understand and remember than assignment propositions. All right, assignment propositions is that one is a lot easier than this. This is quite complex in a way, right? Complex in a way. In one study, the error rate of recalling relational propositions was about 3 times higher than the error rate for assignment propositions. This gives you a general idea about what the two types of what propositions. The main stumbling block in representing many word problems is the student's understanding of part-whole relations. Okay, students have trouble figuring out what is part of what, as evidence in this dialogue between a teacher and a first grader. First grader, that is what must be between 2 to 7, is that right? 2 to 7, PIK, the pre-operational stage, full of fantasies, illogical thinking. So the teacher said, Peter has 3 apples. No, Peter has more. I'm kidding. Peter has 3 apples and also has some apples. So Peter has 3 and some. Peter and Anne have 9 apples altogether. How many apples does Anne have? A simple mathematical problem, is that right? So the student, remember what the student in what pre-operation stage, 9. Okay, 9. The teacher asked, why? Then the student, because you just said so. The student said, well, Peter had 3 apples and also had some apples and had 9 apples. Okay. Peter also has 9 apples. All right. So that's what pre-operational stage. Okay. So here you understand here what the student interprets all together, the whole as each the parts. All together is the whole and each the parts. All right. Okay. Now, understanding the whole problem. Okay, let's take a look at this here. It is quite intriguing. Okay, now understanding the whole problem is you assemble all the relevant information and sentences into an accurate understanding or translation of the total problem. Even if you understand every sentence, you may still misunderstand the problem as a whole. Okay, now take a look at this here. Okay, take a look at this here. You have this overhead, so what you can see it clearly. 2 train stations are 50 miles apart. Okay, at 2 p.m. one Saturday afternoon, 2 trains start toward each other, one from each station. So they are approaching one another. Okay? Just as the trains pull out of the stations, a bird springs into the air in front of the first train and flies ahead to the front of the second train. Now, 2 trains are moving toward one another. Okay, just the bird flies from one train to the other, back and forth. Okay? When the bird reaches the second train, it turns back and flies toward the first train. The bird continues to do this until the trains meet. So if both trains travel at the rate of 25 miles per hour, and the bird flies at 100 miles per hour, how many miles will the bird have flown before the train meet? All right. So you see here, this one here, we have to understand what we have to understand the problem. Okay, what is it? Your interpretation of the problem is called a translation, because you translate the problem into a schema that you understand. Okay, we'll talk about one translation and schema here. If you translated this as a distance problem, okay, and set a goal, I have to figure out how far the bird travels before it meets the oncoming train and turns around, and how far it travels before it has to turn again, and finally add up all the trips back and forth. Wow. If you conceptualize in this way, holy cow, it's gonna be a very difficult problem. Okay, it's gonna be very difficult. But there's a better way to structure the problem. You can represent it as a question of time, right? And focus on the time the bird is in the air. If you figure out how long the bird is in the air, then you can easily determine the distance it will cover, because you know exactly how fast it flies. So the solution should be stated like this. Okay? Now, let's see here, because the stations are 50 miles apart and the trains are moving toward each other at the same speed, the trains will meet in the middle, 25 miles from each station, right, halfway. Because they are traveling 25 miles per hour, it will take the trains 1 hour to reach the meeting point. Right? Okay. So in 1 hour, it takes the trains to meet, two trains to meet. The bird will cover 100 miles because it is flying at 100 miles per hour. It's easy, right? So it depends on how you translate the problem, okay? And then what? And then read out irrelevant information. So let's take a look at translation and what? Schema training, right? To improve translation and schema selection, we often have to move from general to area-specific problem-solving strategies. We move from general to what's specific, okay? The common practice of showing students a few examples, then having students work on many problems on their own is less effective. But then what? This strategy has been very common among school teachers. Well, anyway, let's get back to it. So especially when problems are unfamiliar or difficult, worked out examples are helpful. Right? The most effective examples seem to be those that do not require students to integrate several sources of information, such as a diagram and a set of statements about the problem. This kind of attention splitting may put too much strain on the working memory, especially for a younger child. Remember, they will have what? They will have to what? They will have to pay attention to what? To say part of the memory is used to paying attention, that type of thing, right? Also, when students are learning, worked examples should deal with one source of information at a time. All right. So let's take a look at Meyer, 1973. has recommended giving students practice in the following. Okay, so here, recognizing and categorizing a variety of problem types. So it's the categorizing, you know, that categorizing is very important. Okay, later on, we'll talk about this in what Bruner's theory. Representing problems either concretely in pictures, the best symbols or graphs, or in words. Of course, here, pictures, well, one picture is more than 1,000 words. See words here. Symbols, yeah, symbol. If what the symbols, sometimes the symbol represents a lot, is that right? Graph, of course, graph is like one, more like a picture, is that right? And selecting relevant and irrelevant information in problem. Right? Now, you see here, English is one. Our English is quite unique. And as a matter of fact, all languages are quite unique. Okay? I like to, let me see, I will have to, let me see. All right, now, okay. I'm just trying to see when should I stop, okay? I will make say 1 hour, say a little bit longer than 1 hour, and then I stop, okay? All right, so let's take a look at this here, okay? Now, we mentioned that translation and shimmer training. We mentioned understanding the words, the linguistic comprehension. Okay, let me read you something. Okay, it is a poem. Okay, it is a poem, and just to show you the uniqueness of English language, but not just English language. French, the same, Spanish, Korean, Chinese, Japanese, the same, okay, the same. But then, let me read you this poem, okay? So let's face it, English is a stupid language. There is no egg in the eggplant, no ham in the hamburger, and neither pine nor apple in the pineapple. English muffins were not invented in England. French fries were not invented in France. We sometimes take English for granted, but if we examine its paradoxes, we find that quicksand takes you down slowly. Boxing rings are square, and the guinea pig is neither from Guinea nor is it a pig. So if writers write, how come fingers don't think? If the plural of tooth is teeth, shouldn't the plural of phone booth be phone beef? If the teacher taught, why didn't the preacher prot? If a vegetarian eats vegetables, what the heck does the humanitarian eat? So why do people recite at a play, yet play at a recital? Park on driveways and drive on parkways, like Toronto Starbury Parkway. You have to marvel at the unique lunacy of a language where a house can burn up as it burns down, and in which you feel a foam by filling it out and a bell is only heard once it goes. English was invented by people, not computers. And it reflects the creativity of the human race, which of course isn't a race at all. That is why when the stars are out, they are visible. But when the lights are out, they are invisible. And why it is that when I wind up my watch, it starts. But when I wind up this poem, it ends at the end of this one, of this poem. Isn't it beautiful? Okay, beautifully written, is that right? And the lunacy of the language, it appears, it is what? It is everywhere, okay? It is everywhere. Chinese are like that, and Japanese, okay, all of them like that, all right? Okay, all right. E, exploring possible what strategies. Now, in conducting your search for a solution, you have available two kinds of procedures. Algorithmic, and heuristic. Okay, algorithm. An algorithm is a step-by-step prescription for achieving a goal. It usually is domain specific, that is tied to a particular subject area. So a lot of teachers would put down what the following algorithm on the board at the start of the semester. Okay, so the authoritarian teacher will put down, okay, let me put down what the rules. 1, I'm always right. 2, if I'm wrong, C1. This is an algorithm, very simple, right? Anyway, now heuristic. Heuristic is a general strategy based on reasoning or part experience, okay, that might lead to the right answer. Okay, so that's a heuristic. Okay, all right. So let's take a look at what. Take a look at somewhat possible solution strategies. Okay, A, means ends analysis. The problem is divided into a number of intermediate goals or sub-goals. Then a means of solving each is figured out. All right. Now, I'll give you an example. To write a term paper, you select a topic, like our assignment 1, locate sources of information, see assignment 1, organizing the information, making an outline, and then follow the outline and write, that type of thing. All right, so that the means ends analysis. Now, a second aspect of means ends analysis is distance reduction, or pursuing a path that moves directly toward the final goal. For example, to write a term paper, you could follow a review paper which contains most of the information you need, right? That type of thing. And of course, you learn from the review paper, which gives you a lot of ideas, is that right? So that the ideas may form the outline and so on. All right. Working backwards strategy. You begin at the goal. The goal and move back to the unsolved initial problem. This is true a lot of time in math, is that right? Math, okay, you could do that. Analogical thinking, but this limits your search for solutions to situations that have something in common with the one you currently face. For example, an infection is like a war. Is that right? There, that is one. The virus comes inside your body, but then your T cells are fighting them. So that's a war between the virus and your immune T cells. A stomach is like a blender, is that right? Oh, that is very true. Okay, everything is in there and all blended together. All right, so that's analogical thinking. Okay, by doing this here, this one lends support for understanding the situation. Okay, verbalization. You're putting your problem-solving plan into words and giving reasons for selecting it can lead to successful problem solving. Well, you may have discovered the effectiveness of this verbalization process accidentally when a solution popped into your head as you were explaining a problem to someone else. Okay, and what it was, researcher has found that 9th to 10th grade students were instructed to state the reason for each step they were taking. Okay, they were much more successful in solving the problem than students who did not state reasons. Okay, so verbalization helps. Okay. AL, ideal, IDE, and AL, anticipating, acting, and looking back. Here, after representing the problem and exploring possible solutions, the next step is what? Select a solution. Then anticipate the consequences. After what? After you choose a solution strategy and implement it, okay, then you evaluate the results by checking for evidence that confirms or contradicts your solution. So this is one IDEL. Okay, let me see if I could finish all this within an hour. No. I think I'll stop here. I'll continue in the next video. Thank you.